Looking at the Giza Plateau, the physical mass of these structures commands total attention. Built by the ancient Egyptians, this civilization maintained its presence along the Nile for roughly 3,000 years, from 3100 BC to 30 BC. Yet placing the largest stone structures of antiquity directly in the middle of a barren, resource-starved desert presents a severe geographic contradiction. Archaeological consensus defines these buildings as royal tombs, but analyzing them strictly through an engineering lens reveals a very different problem set. A stone structure of this magnitude operates as a lagging indicator. It is the final, visible result of vast, unseen technological systems. The desert environment is highly restrictive. Without water, crops do not grow. Without paved infrastructure, heavy materials do not move. To overcome these physical constraints, an administration must establish flawless, civilization-wide logistical planning before a single block of limestone is ever cut from a quarry. Committing to a decades-long construction project in an arid climate requires a society to achieve total mastery over its environment and material resources first. To understand how they achieved this, we have to reverse engineer the final structure and work backward from the completed monument. Now, if we peel away the limestone casing, the physical monument breaks down into three interdependent conceptual layers. The top layer is applied mathematics and architectural planning. Below that is the data management layer, required to run vast logistical information systems. And at the absolute foundation is hydrology, the mechanism for generating a massive caloric energy surplus. These three nodes operate together. A critical failure in any single layer triggers a total systemic collapse of the entire construction project. Decoding these invisible logistical and agricultural systems is a mandatory step to understanding how the stones were actually moved. Starting at the top layer, the completed architecture presents an immediate physical challenge. The project requires lifting and stacking millions of heavy stone blocks to a height of over 400 feet without causing the structure to collapse. This introduces a strict engineering problem known as static load distribution. As millions of tons of limestone are stacked higher, gravity acts exponentially on the mass, forcing the pressure outward and threatening to blow out the bottom rows. Looking at this cross-section, the downward gravitational force converts into outward horizontal stress vectors. To prevent structural failure, the exterior walls must be built at an exact incline, roughly 51 degrees, to perfectly neutralize that outward pressure. Resolving this massive stress required the deployment of abstract geometry and trigonometric ratios. For the architects of the Old Kingdom, mathematics was not a theoretical philosophy. It was a daily applied tool for structural survival. This strict mathematical discipline scaled outward into all their project planning, dictating how they organized labor and managed timelines. The precise architecture of the completed pyramid stands as a physical manifestation of this rigorous calculation. Moving down to the second layer, the focus shifts from static rock to the dynamic, living workforce required to assemble it. Housing, feeding, and directing tens of thousands of specialized laborers over several decades creates a massive administrative bottleneck. A labor force of this density quickly dissolves into chaos without a centralized information system to coordinate their movements. This grid of carved symbols represents their primary database. Operating as detailed ledgers, these horizontal registers tracked continuous logistical inputs for the entire civilization. They recorded material supply chains, tallied daily agricultural yields, and maintained exact labor rosters. Beyond simple accounting, this data system had to mitigate the single greatest threat to construction, the physical breakdown of the workers. To manage this, the Egyptians integrated health metrics directly into their administrative record-keeping. By documenting injury recovery times and treatments in the same script used for grain ledgers, their medical knowledge became a technical manual for maximizing labor efficiency. Together, this detailed data logging and medical resource management formed the logistical software necessary to keep the hardware of construction running. The base of this entire system rests on a single constraint, the energy source that powered the operation.
In antiquity, energy meant raw human labor, and human labor ran entirely on massive amounts of agricultural calories. Every major settlement and construction site is anchored directly to the edge of the water, sharply divided from the surrounding dry terrain. The Nile River acted as the biological engine for the entire region. However, the natural annual flooding of the river is highly volatile. To be useful at scale, the water volume had to be actively captured and distributed. This mechanism, known as a shaduf, utilizes a counterweight to manually lift water out of the riverbed and onto higher elevation. Implementing mechanical irrigation systems was the society's first critical engineering threshold. Viewing this topographical map, the Nile appears as a narrow corridor of potential energy trapped within an arid wasteland. By cutting artificial channels and basins branching outward from the main river, the administration systematically expanded the energy grid. This controlled manipulation of the floodwaters mathematically correlated to an exponential increase in grain yields. Generating a massive caloric surplus allowed a specific percentage of the population to stop farming entirely, freeing them to become the specialized builders, mathematicians, and doctors required for monumental construction. Hydrological engineering is the exact mechanism that generated the labor surplus. Water management is the literal foundation that allowed the pyramids to be built. With the three components identified, we can run the civilization's analytical model forward. The entire process moves sequentially forward from initial energy generation to complex data processing and finally solidifies into a completed stone monument. The engineered Nile generates the caloric energy required to sustain a massive, specialized labor force. The hieroglyphic database tracks and allocates those calories, raw materials, and manpower with exact precision. Applied mathematics then directs that organized labor to safely stack millions of tons of limestone. The Great Pyramid is the predictable, calculated output of a highly optimized, civilization-wide supply chain. This systems-level approach allowed the Egyptian civilization to operate efficiently for nearly 3 millennia. Today, the monumental stones remain on the plateau, but the dynamic networks that built them have long since vanished. This society conquered the logistical challenges of the Nile Valley by first organizing its social and material reality into a single functional system. They successfully integrated large-scale hydrology, complex data management, and the physical sciences into a single cohesive engine. It is the combination of these disciplines that proves their capacity for advanced engineering. Ultimately, ancient Egypt's most significant legacy is the invisible blueprint of systems engineering they left behind.